Hello, class. It's taken me a little while to get organized today because, it is the summer, and instead of me being outside at the beach getting coronavirus, I'm inside doing a lot of these lectures. So, trying to get everything, set up just like I did for the summer, so that I had, I knew where everyone was going. I could give, out home sets and labs. I think the labs are going to be the hardest part over the summer. I didn't have to do labs with that course. It was just electromagnetic field theory is just a lecture course. So, let's get as many of these done as we can so I know exactly where you're going and how to do it. And that way it'll be easier on all of us. So, today I want to start friction. And friction is a larger topical area than, it'd be like centroids or mass moments of inertia or area moments of inertia, things that you're going to use in your engineering career. I should turn that light on. This is my first lecture of the day. Should turn that light on to give it a little more light on the board here. But like I say, friction is a big area, and so I'm going to spend some time talking about it, and we're going to be doing some problems and everything else to, understand how friction, both static friction and kinetic friction, work in our everyday lives, right? And every mechanical engineer has this as, one of the beginning parts of their statics course, because it really falls into static equilibrium and dynamic equilibrium, which I'm going to actually look at a very, short problem first, here. And, but first I want to introduce, what friction is. And when you think of friction in the most elemental form, I've got some type of rigid body, right, on top of a plane of some kind. And then that body is producing a weight force on that. I mean, if we're talking about bodies at the surface of the Earth. So I've got a weight force that's working down. If I wanted to move that, whether it to the left or to the right, let's just say I'm going to put a force here that would move that, right, to the left. And I should really make these vectors because they are vectors. Forces are vectors. And then I would have a force that's restraining that motion. And just like I said in that example that I did before this in the last lecture, we usually define that force as F sub r. I'll write it as a vector, but whatever. So this is some applied force, and this is my frictional force that's reacting against that applied force that's trying to cause motion. Now, how can we figure out what F sub r is? F sub r, the magnitude of F sub r, is in the beginning, and I should say that this would be the static F sub r, is going to be mu sub s times n. N being the normal force that's working against this. If I drew this as a free body diagram, well, if F sub r equals F sub a, well, that's an equilibrium in the x direction, isn't it? But what's opposing the weight force? Well, there's an equal and opposite force there called the normal force, isn't there? Excuse me, I'll just have a sip of water here. So it's mu sub s times the normal force. And you're saying, well, the normal force equals the weight force. And that's not always true. That is not always true. And that's only true when it's drawn horizontal and the thing is sitting on a perfectly flat plate here, isn't it? What if instead it wasn't? Oh, wait, I'm getting ahead of myself. Because, this is mu sub s, and you're probably saying mu sub s, what does the s stand for? Mu sub s equals the coefficient of static friction. And we've got another one, mu sub k, that is the coefficient of kinetic friction. Right? Now, mu sub k is always less than mu sub s. So mu sub k is less than mu sub s. That's all that we can really say about that, though. Can't say that there's a certain, relationship between the two. Different surfaces with different types of lubricants are going to have different ratios of mu sub s to mu sub k. So I can't really say, but I can always say that mu sub k is less than mu sub s. And in fact, here's what happens. Let's say that I'm looking at a situation like this that I've got up here, right, with W and everything else, and F sub r, and I'm just going to draw a little graph, right? Now this is going to be F sub r, right? That's my frictional force. And this is going to be the force F sub A. And so now as I increase F sub A, doesn't F sub R increase at the same, because let's face it, if F sub A is 0, if that doesn't exist there at all, what's F sub R? 0, right? Let's say that I just put a little string on that 150-pound weight, and I just sort of tug on it a little bit. Well, then it's not going to move, is it? So then F sub A and F sub R grows as F sub A is applied. F sub R grows as F sub A is applied, and it grows in a one-to-one fashion. So I apply a little dash of F sub A, and F sub R reacts to it and stops the thing from moving, right? And then I push it a little more, and F sub R is still pushing back. So the higher that I go on my applied force, the higher the frictional force goes to oppose me, right? And everybody's done this. You're pushing on a file cabinet, right? Or you're pushing on a table or something. And as you push on it, you can't get it to move, right? So it constantly is pushing back with the same force that you're pushing on it until it moves. As soon as you start pushing on it and it moves, then you're going to keep pushing on it with the same force, right? You're going to keep pushing on it with the same force, but the frictional force immediately comes down. And then that frictional force remains at that lower level no matter how much more force you're going to apply to it, right? Let's say that you're moving a table across a kitchen floor. You start to push on the table. Now, as you push on the table, it pushes back until it reaches this point right here. And what is that point? That point is mu sub s times the weight of the table, because I'm talking about a table on a kitchen floor, so I'm talking about relatively a flat floor. I mean, why would you not have a flat floor in a kitchen? I know, that wouldn't make sense. So the normal force pushing back against it is just like this here, right? So the weight force equals the normal force in this case. But once I get to that point, it then drops. It's easier for me to push the kitchen table across the floor once I get it moving. Once I get it moving. And so when I do get it moving, it's then a lower force. I bet you didn't even know that, did you? I'm not even sure I knew it. You know, I might have intuitively known it, but, you know, thought, well, it's, I must not have that right. I remember I never got boiling water right. My neighbor said, that's not how boiling water works, son. And he fixed it right up for me. That was great about having an engineer dad. Now that's all red, supposedly. I hope everybody can see that's red. Now, what is that level right there? That level is mu sub k times n. Does everybody see that? And really, when I draw these, I should be drawing probably the absolute values around them or whatever, but not in the free body case, but you know, in these cases. But we're only talking about two-dimensional representation here anyway. So with only one singular frictional force working against it. So this level here is going to be the new force. And you can see the difference. If I was to continue that force A right at that point right there, what would be the difference? What would be the acceleration? The differential in this force, right? And if you look down here, you'll see that I'm still applying, like f of a is still going up, right? So I'm not only accelerating this thing with a force via its mass, but I'm accelerating the acceleration if I kept increasing f sub a. If I just kept f sub a here, f sub r is going to go down, right? But f sub a is still going to stay the same. So what would be the differential? This differential here of delta F is going to equal mass times the acceleration of the table across the kitchen floor. Does everyone see that? Does everyone see how this all manifests both in static equilibrium and dynamic equilibrium? Excellent. That's my catchphrase, by the way, if you ever had me in class in reality. You probably would hear me say that. I'm going crazy. I've done like, 20 lectures in a week. So let's look at a problem, but not a problem that's easy like this. Let's look at a problem that is a little more complicated. And so here's what I want to do. I'm going to make a 30-degree incline, right? So I've got a 30-degree incline here. I'll say that's 30 degrees. Doesn't that look 30 degrees? I don't know. I have a 30-degree thing around. I'm not going to get it. I'm assuming that's 30 degrees or something like 30 degrees. All right. I'm just going to draw this up here a little further, and then it's going to sort of fall off because I'm going to put a box on here. And that box is going to weigh 200 kilograms. Now I said weigh, but I really mean the mass of the box is going to be 200 kilograms. And I know in your head, you're already figuring out what the weight of 200 kilograms would be as a weight force rather than as a mass, right? Now, I'm also going to set up a little, pulley here. I'm going to set up a little pulley there, and I'm going to put a tension line on here, and I'm going to put the tension line on here where I can put some type of weight, right? Whatever that weight is. That weight is going to manifest some type of force. So we could call it force due to the weight. You know, what should I call that? Maybe, you know what, I'm just going to call it F. We don't have any other F, so why not just call it F? We'll call it F this time rather than F sub anything else. But I think that what you can see is in this diagram, there's going to be two components of the weight force, right? There's going to be a component of the weight force. Boy, I drew that in the wrong location, that 200 kilograms, didn't I? You know, that's fine because it's like having an eraser, guys. So I've got two different components. I've told you before how happy I was that I actually fixed this, right? Fixed, you know, saved my dollar. Boy, I've got so much correct type in there. So we've got two different. I'm going to call this W sub N, and I'm going to call this W sub T. That would be for the normal to the surface, the weight component that's normal to the surface, and then the weight component that's tangential to the surface. I think everybody can see that. Not only that, because I've got that weight component normal to the surface, I also have, right, an equal and opposite restraining force called my normal force. And I, of course, got this tension in this line here. So really, this is going to be, I mean, what's pulling up here is going to be F, right? So why don't we redraw that? Now that we see how the picture, so this is the picture, but it's not the free body diagram, is it? No. And as a matter of fact, what we want to do is we want to make it into a free body diagram. And so let's just draw it like it is. I've got a box. I've got a force off the end of the box that I'm going to call, you know, should I call that, let's see, yep, I'll call that F. And we can differentiate between F and F sub S and F sub K later on when we do it for static equilibrium analysis and for dynamic equilibrium analysis, all right? But right now we're just going to do this. I also have W sub N that I can figure out, and opposing it, I've got N. Going in this direction, I have W sub T, right? Does everyone see how my free body diagram now has reoriented all of my things, and I now am using the forces that I've already broken into components into this? So I want to answer two things. In this configuration, A, will it slide downhill? You know, I haven't given you some pertinent information here. I'm going to have to do that first. So the pertinent information, you know, is that mu sub S equals 0.6, and mu sub K, the kinetic coefficient of friction, equals 0.3. Now you're probably saying, how does that correspond to rubber on concrete, right? So rubber on concrete, dry. Rubber on concrete dry is 0.4 to 0.7. That's a 7. Yes, it is. 0.4 to 0.7. Leather on metal. Leather on metal. Now you're probably saying, well, when does that happen? You know, they used to have clutches like that, leather on metal, about 0.6, and that's dry. So, you know, we're talking about the same rubber on concrete, leather on metal, about 0.6. If I have steel on steel, now, when would I have this? Well, if I had a pile of powdered steel, the coefficient of static friction is 0.8. So if I had a pile of powdered steel, that pile of powdered steel would be uh, pretty close to 45-degree angle as far as the angle of repose goes. But aluminum on aluminum is 1.35. So you're saying yes. Yes, that means it's even over 45 degrees. So if I had a pile of powdered aluminum, it would be standing up like a cone with an angle of repose for that pile larger than 45 degrees. Right? Interesting. Also, if these were lubricated, for instance, if this was lubricated, let me just put another thing up here, lubricated. This rubber on concrete, and when I say lubricated, I really mean ice or water. You know, this could go down to about 0.15, even lower if you're right on a sheet of ice, which of course then is not rubber on concrete, it is rubber on ice. Good question there. You're probably asking yourself, why does a large car not slide as far on an icy road as a small car, right? That's going the same speed when they apply their brakes, and their brakes are sliding and their wheels are sliding on the ice. Because you'd think, well, you know, the smaller car, the lighter car has less momentum, but it you know, slides further than the smaller. They both should slide at exactly the same distance, dependent, you know, irrespective of how you do the analysis. If they have the same coefficient of friction between the tire and the ice, they should both stop in the same distance. Go ahead and work that out if you want to with momentum and everything else, but it works out that way. Now, why is this not true? The thing is that the larger car, the heavier car, actually, because of its weight on the tires, which isn't that much greater because the weight of the car goes up by its volume and you know, everything in it, whereas the tire on the road only goes up as the square or the square root of that. So it actually liquefies the ice more and changes the ice and uses the indentations in the ice differently. So the effective coefficient of friction for a large car is much higher than even kinetic coefficient of friction is much higher than it is for a small car, which is really just sailing along on top of the ice. Whereas the larger car, you know, penetrates and you know, cracks the ice and stuff like this differently. And so there's the difference if you wanted to actually, you know, find that out. However, I'm getting a little bit off topic here. Let's actually figure out what this is. Is it going to go down the hill? Well, we know it's 0.6 and we know what this is. So let's figure out what these are. Now we know that's 30 degrees. So what would this angle be right here? And you know how I do that? Let's say that I had a pendulum that was hanging, right? I have a pendulum that's hanging from this. Now, as I start to incline, right, because that pendulum is hanging like the weight, right? So as I start to incline my plane, how does that angle change? How does the angle, look at the angle between my thumb. I don't know if I can really do that, right? How does that angle change? it changes the same as the angle coming up, doesn't it? So as this angle comes up, that pendulum would then swing the same amount. So this also is 30 degrees. Does everybody see that? Now, where did I put that? Right. Okay. So W sub n is going to be the cosine of 30 degrees. So W sub n equals my weight force. And I think everybody has seen that my actual weight force there, weight, did I do it over? Okay, whatever. I'll do it. So the weight that we're going to have is 200 kilograms times 9.81 meters per second squared. I always want to put your units on there. So that is 1960. I'm just going to say 1960 newtons. All right. So 1960 newtons, I've rounded it there a little bit instead of 1962, times the cosine of 30 degrees. All right. And if I, this is really just giving us the component of the weight force in the normal direction. And if we plug that in, I'm sure that I'm going to get 981. Yes, I should use 62, shouldn't I? Sure, okay, there's 62. I'm using 62. All right, so, oh no, that's not gonna, the sine of that's gonna give me, let me do that one too. So W sub t is going to be 1960 newtons times the sine of 30 degrees. Sorry about that. And that gives me 981 newtons for that. And 1960 times the cosine, oh, didn't turn it on. 1960 times the cosine of 30 degrees equals 1697. I have 1699 there for some reason. I'm not sure. There's a 1962. Maybe that was it. Times the sine of 30 degrees. Oops. Okay, 1962 times the cosine of 30 degrees is 1699. So I better just go with my original working out of the problem and not cutting any corners here. So that's 1699 newtons. And then W sub t is 981 newtons. So let's just see if this is, oh, you know what I forgot? We're looking at it going downhill first, right? So for this iteration, it's going to be working against it sliding down, isn't it? The F sub r is going to be going against it sliding down. This is the first iteration, right? Is it sliding downhill? The second thing I want to ask is if it's not sliding downhill, right? How much force, F, do we need to pull it uphill? How much force is necessary to pull it up the hill, right? With our conditions of mu sub s and mu sub k. And the third thing that I want to know, C, is what is the acceleration up that hill, right? What's the acceleration in meters per second squared if it is moving? So I've sort of let the cat out of the bag, right? I think we're going to find out it's not sliding downhill. And then we're going to find out that, well, it takes quite a bit to pull that uphill. And then we're going to find out once it starts moving uphill, if we continued that force. So if F equals a constant after it starts moving, what's the acceleration of that package going to be up that ramp? That's what I want to find out. All right, so we know that W sub t, the force that's pushing it down here, is going to be 981 newtons. Now we can, and we know what W sub n is, and we know that W sub n equals n, right? The normal force. So we can say that 0.6 times n, which of course this equals n, 1699 newtons. And that gives me 1099.5 or 1019.5. And I hope everybody's doing this with their calculator along with me, because that's how we really do it in class too. So let's just look at that. Well, we've got 981 pulling it downhill, and we have to overcome the maximum, right? Oh, wait a second, what have we got here? I'm going to put mu sub s and mu sub s there. There we go. Because the 1699, of course, is n and w sub n over here. That's what the 1699 is, and of course, that's what I was doing here anyway. So this is going to be F sub r maximum. Remember here, right? So we have to, for it to go downhill, we would have to have more force applied, right, than the maximum force that we would get here. And of course, the maximum force that we can get resisting motion is 1019.5, but we've only got 981 newtons working to go downhill. So if we look at this, we see that I've got 981. Let's say that F is 0, right? F is 0. So if no force is applied, that's what I really should put here. Does it slide down here? If F equals 0 newtons, right? If no force is applied, is this going to just slide down the hill? And the answer is no. Give me a red pen. The answer is no. It's not going to slide downhill, right? What's the second one? What's the force that I need to pull it uphill? Well, let's say that I do want to pull it uphill. Well, this F sub r no longer would be pointing in that direction, would it? F sub r would be pointing in this direction against the impending motion. So what I would need for the force to pull it uphill, I'm going to actually write this out here, force to pull it uphill would be to overcome W sub t, right? W sub t is still pulling it downhill. That's the tangential weight force that's pulling it downhill, right? I would have to overcome F sub r too, because F sub r now is working against the impending motion, and the impending motion that I'm going to have is in this direction. I'm increasing F. So as I keep increasing F, I've still got to work against that too. So that would be F sub r max, wouldn't it? So I have to overcome those two forces. So let's see what that comes out to. W sub t, we know is 981 newtons. F sub r max, right? Still going to have the same normal force and everything pushing down there. So it's still going to be 1019.5 newtons. So to start pulling this uphill, I'm going to need 2,000. Why to put the 0.5 in there? 0.5 newtons. Does everyone see that? And as soon as I get to 2,000.5 newtons, what's going to happen? Motion. So at 2,000, so at 2,000 newtons, motion. Motion at 2,000 newtons motion. But at 2,000 newtons, let's just see what happens. Now all of a sudden, F sub r kinetic is going to be 0.3 times 1699 newtons, right? So 0.3, so it's going to be 1/2 of 1019.5, which is 509.7. Does everyone see that? So we're all of a sudden gaining 509.7 here, because now at 2,000, what is that's what F sub r max is. So the total force opposing it uphill kinetically is only going to be well, that's not right. Wait a second. Minus 509.7, all right, is 1490, right? So up the kinetically uphill, it's only going to have 1490.8 newtons that it needs. So the extra 509.7 newtons that it's got is going to turn into acceleration, because F equals ma, right? F equals ma. So A is going to be F over m. We know that F, the extra F, is going to be 509. This is if you kept pushing at the same force. And we know m is 200 kilograms. I hope everybody can see that. I think you can. So 509.7 divided by 200 kilograms means this will be accelerating at 2.5 meters per second squared, which is a pretty good acceleration, right? So once that thing starts moving, it's really going to take off, right? It's almost like you've got something that's on a slope that is on a very rough surface, and then you've thrown oil in front of it, right? And that oil is just seeping underneath that, and eventually it's going to cause it to start moving. And once it does start moving and start moving entirely over the oil, then it's going to go down to 0.3, and it's really going to slide, right? That's a huge difference between mu sub s and mu sub k. And that's what you find out there. All right, that is done with our intro to friction. We're going to have about 3, I would think, lectures, maybe 4 lectures on friction, maybe 3, who knows? We'll see. It's a great area to understand and cover anyway. All right, see you at the next lecture.